Hello everyone, it's 1 p.m. Eastern, and that means it's time to begin another of our monthly CoCoRaHS Weather Talk webinars. Thank you for joining us today. I'm your host, Henry Regis, and behind the scenes, running the technical side of our program today, is Noah Newman. We're coming to you live from the Colorado Climate Center here in sunny Fort Collins, Colorado. We're located at Colorado State University in Fort Collins. For those of you who are unable to join us for our live broadcast, we'll be recording it for future viewing on our website. All of our Weather Talk webinars are sponsored by grants from NOAA's Office of Education and the National Science Foundation. Today's webinar will look at atmospheric rivers. To some of you, that may be a new term, but I'm sure that by the end of this webinar, you'll know that term very well. And we're excited to have with us today Marty Ralph. Marty is a synoptic and mesoscale research meteorologist who focuses on understanding the physical processes that create extremes of precipitation ranging from flood to drought, and on advancing associated observations, predictions, climate projections, and decision support tools. From 2001 to 13, Marty was the chief of the water cycle branch of NOAA's Earth System Research Laboratory in Colorado, where he led the development of the hydrometeorology testbed. He also managed NOAA's Science, Technology, and Infusion Program, chaired NOAA's U.S. Weather Research Program Executive Committee, and led the creation of NOAA's Unmanned Aircraft Systems Program. In 2013, he moved to the University of California, San Diego Scripps Institute of Oceanography, where he is developing the Center for Western Weather and Water Extremes. Originally from Detroit, Marty is a Detroit Lions fan. Welcome, Marty. It's great to have you with us today. Hey, Marty, tell us a little bit about how you became interested in atmospheric rivers. You mentioned it goes back to your younger days moving from Detroit to the desert Southwest.
Yeah, hi, and thank you very much for interest in this subject here. Yeah, I got into weather as a youngster moving from Detroit, suburban Detroit, Michigan, where you couldn't see the forest for the trees, to a hilltop in southern Arizona on the border with Mexico, and could see storms coming 100 miles away, literally, and then see the rivers flow in what is otherwise sort of a desert environment. So it really got me tuned in to the importance of precipitation and the water cycle on wildlife and the environment, and it's fascinating to watch on a day-to-day basis. So that's where this sort of a career came from.
Well, thanks, Marty. I'm going to pass it off to you now, and if you'll give your presentation, that'll be great.
Okay. So the title here is Atmospheric Rivers, and this is an overview for CoCoRaHS participants. And the photo here is actually from Northern California, from a colleague, Paul Neiman, as a storm was hitting the coast there a few years back, and you can see the gorgeous mountains reaching the coast there, and the river coming out of the mountains there behind the rain. And you also see the very lush green hillsides. This is a place right now, for example, if I were to take a picture today, those hills would be completely brown because we're experiencing the worst drought on record in this very area just north of San Francisco, where this picture was from. And we'll talk about in a moment the relationship between atmospheric rivers and drought. Okay. There we go. So I'm going to give you a little bit of a history of where we learned about this stuff initially, and some initial papers, and then some recent results, some future directions, and hopefully, if time permits, a little bit about what's going on right now on the West Coast in particular. So this image represents a result from what I consider to be the seminal paper on atmospheric rivers by investigators Zhu and Newell, published in 1998 in Monthly Weather Review. They're from MIT, and they looked at global weather model for about 2 years and found that about 90% of all the water vapor transport in the atmosphere in the mid-latitudes took place in relatively narrow regions, which they termed atmospheric rivers. They came up with the jargon in the 90s. And it turns out that there are on average 3 or 4 of these in a given hemisphere at any moment. And if you add up the width of all the ARs in the hemisphere at one time, it's only about 10% of the circumference of the Earth. What that means is they're very narrow filaments of atmosphere that are moving most of the water vapor. And we'll show a lot more about that here in just a moment. So one of the reasons we
Marty,
learned, yeah, go ahead.
excuse me, I'm sorry. So it looks like part of your screen is cut off here. I'm not sure how you're doing in presentation mode here, but yeah, let's see if we can try it
Yeah,
again. And it's
there's a resolution issue, and I've got to somehow get to my control panel.
right, and I'm not sure if a function F8 or F7 or one of those F buttons will change the resolution. We can see your home page, start page right now, I guess, but
Yeah, I struggle to find the to get to my control panel with my new computer here. So maybe I can do this.
What if he hit the show slideshow button that was on that last one?
yeah, and if you do that and then you do control plus and the minus button, it can minimize it. It'll shrink it a little bit and possibly get it into the view too.
Could you step me through that again? I don't see the
Sure.
button
So
you're talking about.
if you can start your slide presentation again, like show your slides and then start the presentation.
Okay.
Yep. Now if you hold the control and then the minus, which is kind of two buttons to the left of your backspace button, just to the right of the 0.
Yeah, I just did that.
Okay. Yeah. And that's a different function on that computer. So that was my best guess on trying to shrink it a little bit, but that it looked good for just a second there. Well, we might just have to suffer with only seeing the upper portion, the upper left-hand portion of your screen. We're not missing all of it, but
How much of it can you see?
well, it cuts off at the bottom, right at 50 degrees south.
Okay, but can you see the full left and right?
We can just barely make out the numbers on the right side of the screen. We can see 50.
Well, I don't think I have a choice here,
Okay.
unless you want to reschedule or something, because
Yeah.
I don't know how to switch the resolution on the fly here.
Okay, let's go what we got.
All righty. So some of these that'll work just fine. If it's if you can't see what I'm talking about, I'll just move forward to something else. So so this is all right. So restart. One of the reasons we were able to learn more about these in the last several years is the advent of some new satellite imagery. And can you see my cursor on the screen?
Yes, we can.
Okay, so this is an infrared satellite image of the eastern Pacific, and you can see the part of the storm that people have been paying attention to for a long time with the cold cloud tops up here, and then you don't see much down this way. If we go to what's called the water vapor channel, which is unusual part of this type of satellite imagery, it gives you water vapor, but it's only in the very upper atmosphere, and you don't really see much else there. But if we go to this new type of satellite data called SSMI, it gives us the integrated water vapor in the atmosphere. And here you see this ribbon of orange. That represents large water vapor contents. Blue is sort of dry, and down in the south here is the tropics, which are very moist. So we came to recognize this signature of long, narrow region of large integrated water vapor content as an indicator of AR conditions. And in the red, I've highlighted that here, and that's the area we couldn't really see in the normal satellite data. This is now a loop of satellite imagery from storm about 2 years ago, and you see the very dynamic nature of the atmosphere. And the variable shown here is the integrated water vapor again, where we've got this orange color is very wet, red's very wet, and you can see in the tropics at the bottom here, the air's moving from right to left, east to west. But in the mid-latitudes, it's from west to east. And you see these surges of water vapor heading poleward or eastward. There's one that hit the Bay Area, then another one, and it stalled. Then it cleared out. Then another one came and hit it. In the time period of this several-day period, this area where the cursor is in Northern California, some places got over 20 inches of rain in about 3 days. And this is what ARs can do when they stall over a place or you get multiple ARs hitting over a short period of time. All right, one of the other ways we learned about this was through use of research aircraft. You can see the NOAA Hurricane Hunter on the lower left there. We used it one winter in the late 90s to measure a storm off the west coast. Here's California, and here's one spot where we happened to fly the P3. And notice the low pressure center way up here to the north off of Vancouver Island. This is one of the other things we've learned, is that the AR conditions are really well displaced from the low center itself. And where that hits the coast is where the heaviest rain occurs. The sketch on the right is really just a flight plan we used for the P3. The findings from that experiment, and combined with the satellite data and combined with the aircraft satellite data and that Zhu and Newell finding, the light bulb went off for us around 2003 or so, that what we were really looking at was atmospheric rivers. And this is a schematic showing a low pressure center, the occluded front, the cold front, and stationary front. And this cross section from A to A prime is where we had aircraft data. And this is a schematic showing the integrated water vapor from the satellite imagery composited over many cases. So you see how narrow that integrated water vapor is. We didn't know if that water vapor signature was really going to be representative of where the transport was large, because the water vapor content, well, it's just the water vapor. It's not the winds, or it doesn't include the winds. So we needed wind information. That's where the aircraft data came in. And you see here a cross-section from A to A prime. Vertically, we're up to 10 kilometers. And in blue, you see the isotachs, or wind speed contours, and 45 meter per second winds up here at about 30,000 feet. That's where you fly. That's the jet stream, as we usually refer to it. And this is where you fly when you're flying commercial jets. But it turns out the air is so cold up there that it's extremely dry, and it doesn't really transport much water vapor because it's so dry, even though the winds are strong. But if you go down lower here, you see this little blue contour right here is a 25 meter per second low-level jet down here below 1 kilometer altitude, or right at 1 kilometer altitude. And the pink region is the region of strong water vapor transport. The green lines represent water vapor mixing ratio, and you've got lots of water vapor down here with the strong winds, and you multiply those together and you get the strong transport. You see that 80 unit contour right there. And you also see the cold front reaching down from aloft to the surface, and that is the back edge of the AR. So the ARs reside on the leading edge of the cold front, which I'm sure folks are familiar with. Now, the vertical structure of these things from a transport perspective is shown here. We had about 17 aircraft flights over 2 winters, and we, on average, were at this location. We measured the ARs very precisely. And in the bottom, we see a schematic along the AR as the air heads towards the coast. And here you see it going up the coast and creating rain in the Coast Range and the Sierra Nevada. But what we found was that the low-level jet on average was present, and it on average was about 25 meters per second wind speed, or 50 knots. And about 3/4 of the water vapor transport occurred in the lowest, about 5,000 or 8,000 feet, and that the conditions were moist neutral. And what that means really is that the air is primed to just go up over the mountains when it hits the mountains, rather than be blocked and turn along the mountains. So this is why ARs can be so productive in producing precipitation, which I'll turn to right here. So here's a case study. This was really our sort of aha moment about the linkage between ARs and heavy rain and flooding. This satellite image shows a classic AR hitting the coast, and the color-filled dots are the stream gauge data, and the red dots represent a record flow for that day of the year, and yellow is high as well, and all of these color-filled dots are where the runoff was strong. So you see the correlation between where the AR hit the coast and where the heavy runoff was. We actually did this for one case, is what's shown in the left here, but then we asked the question, because we had HMT data, special data on the coast from the hydrometeorology testbed mentioned earlier, we could identify that all 7 floods over the previous 8 years were actually associated with ARs. We've now come to realize that that's true in Washington State, and here's a reference to another paper on that. And this result extends to other regions as well. One of the other things that, and I'll come back to that in just a moment with what we're finding out about ARs in other parts of the country. Because they can produce such heavy rain, which can create a flood problem, it's also true that heavy rain can sometimes be very beneficial, like in the case of now with this drought going on in the West Coast, and California in particular. Some of that heavy rain would be very welcome. And what we did here is we looked at all the AR events over about 10 years and looked at how much of all the rainfall that accumulated at many co-op observer sites in the region could be attributed to ARs during those 10 years. And the color fill on the left, what you see here, for example, is in the 30 to 40% range. All of the rain fell, all of that rain fell in really just a handful of days each year over the 10 years. On average, about 6 or 8 storms or AR events. And you can see how that's true in the Pacific Northwest as well, but with a more like a 25% contribution. The fact that the dots aren't filled in to the east, we'll return to that in just a moment. That has to do with how we did the study. We were looking at when ARs hit landfall, and that really emphasizes the West Coast. But we're learning that ARs penetrate inland as well, and I'll show you some examples of that in a moment. Another thing that they do because of this precipitation role is they can actually be very helpful in relieving drought. And this is a study published by Mike Dettinger, also part of our center here at Scripps, where on average the droughts begin sort of gradually. This is a study keyed on 6 months before and after the month of a drought break, defined by the Palmer Drought Severity Index jumping up from below -2 to 0 or above. And what we see is the gradual decline. These are all average now, the gradual decline into drought over 6 months, and then the rapid jump out of it. It turns out that half of those jumps out, those months, had associated with them strong atmospheric river conditions in that region. Now let's turn for a moment to how do ARs relate to extreme precipitation further inland. So to study this, we looked at the co-op data, the daily totals over anywhere from 30 to 50 years, and each of these dots is a different co-op site where we had at least 30 years of record. And we just asked a very simple question, and this is published in Ralph et al. This year. Very simple question. At each co-op site that had at least 30 years of record, what were the top 10 daily rainfall totals in all of those years? And then we asked what month, what seasons did those events occur in most commonly? And then we color filled the dot according to that season. So the dark blue is January, February, March. So that's where most of those top 10 events occurred in the cool season. Red is October, November, December. And you can see those line up with the cool season AR phenomena. Interestingly, April, May, and June, you can see the light blue is spread more inland and in the north. And then July, August, September, spread around pretty well in the whole Intermountain region and Front Range, and heavy emphasis in the southwest with the summer monsoon. But notice Arizona, for example. Some of these sites, many are yellow, representing the monsoon season as a source of extreme precip. But notice the reds and even some blues intermixed in there. That intrigued us, and we see this also in Idaho and in Colorado and in Idaho, Utah, Colorado, Nevada, and Arizona. And this is something we've learned is really characteristic, that the most extreme events in those regions can come in almost any season. But we can also extract from that what the AR region is in terms of impacts. And you see here a schematic showing the region where we found ARs to be significant sources of extreme events. And it stretches all the way inland into Arizona, Idaho, central Utah, even the west slope of Colorado. And I want to explore that a little bit more with a case study. This is an image of a colleague or friend, actually. We were backpacking in Arizona, a canyon called Aravaipa, a couple of years ago, and this was after a major flood had occurred in early 2010. And that flood was the focus of a study we did that's published here by a paper by Neiman et al., part of a 2-part series. And you can see how high the water must have been. A really beautiful place. If you've ever been to Aravaipa or haven't, I recommend it. So the storm looked like this in the satellite data. This is the SSMI, integrated water vapor. We see an AR hitting the California coast, and then strengthening and coming in, aiming towards Arizona. Notice the continent is dark here. That's because the satellite-based measurement system doesn't work over land, because the emissivity from the land is so variable they can't pick out the water vapor signature from the atmosphere part of the signal. And this is how much precipitation fell in association with this storm. And you can see pinks in here in the 6 to 8 inch range, which is a lot of precipitation for one day in Arizona, having grown up there a bit, as I mentioned earlier. This is a very busy schematic. I just want to highlight the fact that what we see in the red curve here is the core of an AR coming in from the southwest and running up against the terrain. The background color is terrain height, and it runs into terrain, and the yellow area represents where the heaviest rain was. And it turned out that we've now learned that the ARs that come in from this orientation are the ones that can produce the heaviest precipitation in this part of Arizona, and is why they get some of their most serious flooding actually in the winter. An interesting subtlety here is notice the higher mountains sort of in the background here in northern Baja, and they're not as high right here. The follow-on study I mentioned showed with numerical modeling that it's very important that the AR actually got south of that high mountainous area of northern Baja and penetrated in over this very low altitude region before it got to Arizona. That allowed it to not rain out as much and end up producing more rain in Arizona. And this is a subject I won't touch on too much here, but to say that we're learning that there are these pathways between the mountains that AR water vapor transport can get into the Intermountain West, or into the Southwest in this case. And there was a nice study by John Rutz and Jim Steenberg. John just finished his PhD with Jim at University of Utah, and he took and extended the study that myself and Mike Dettinger and Paul Neiman did in the figure on the right. Remember I mentioned that the ARs, when they hit the coast, we sort of keyed on that because we had the satellite data offshore, but we only did it for ARs that hit as far south as the Mexican border. What John did, in a very bright move, was consider ARs that hit Baja. And he and Jim Steenberg were able to conclude that, in fact, this added to the AR impact in the Intermountain West in a significant way. And you can see the change here on the right, where the increase in the atmospheric river fraction of precipitation annually increased substantially. So the red areas here basically represent regions where AR landfall in Baja, or very northern Baja, or even farther south, contributed quite a lot of rainfall to the southwestern U.S., up to 10 or 15% of the annual totals. So we've got to look at the whole West Coast in order to get this right. So another question that we raised was, and I'd had to deal with this for many years, was, okay, Marty, so you're talking to us back here in D.C. and you'd like NOAA to do more work on the West Coast, and I'd tell them how extreme the precipitation was, but it didn't really sink in as much as it could have. So we did this study to look at how extreme precip is in the West versus the Southeast, where people's natural perception is prone to landfalling hurricanes and summer convection in the Midwest and southern states. So this diagram shows the places where the heaviest rainfall events occurred over the last 50 years using co-op data, nearly 60 years. And the way we defined this was 3-day rainfall totals. And we have this categorization scheme we call RCATs for rainfall category. 200 to 300 millimeters in 3 days, that's 8 to 12 inches. Then 12 to 16 inches is RCAT 2, 16 to 20 inches is RCAT 3, and more than 20 inches in 3 days is RCAT 4. Turns out that we get about nationally 2 or 3 co-op gauges nationally would receive that much rain in a year. That's about the equivalent of how many F4 or F5 tornadoes occur each year, or how many major hurricanes occur in the Atlantic. So this category 4 for rainfall is really sort of that extreme of an event. And of course, 8 inches in 24 hours is quite a lot of rain as well. And notice the West Coast here, in particular California, has as many of these red dots as the Southeast. And the dot represents the maximum rainfall category event in the history of that co-op site. So you can see that the West Coast events are as extreme as anywhere else in the country. And those events, as we've just shown, are really primarily due to ARs. it turns out we're learning that some of these events in the southeast are also due to ARs, and I'll show that in just a moment. I did want to highlight for just a second here that this categorization scheme, I'm sort of intrigued about its connection potentially to CoCoRaHS observing, because it'd be very easy to use this categorization as a graphic, for example, with CoCoRaHS data. The key is looking at 72-hour totals. It's not hourly, it's not daily, it's 3 days. And we found 3 days to be the sweet spot for the most extreme events. If we took 4 days, using the co-op data, we found that the driest of the 4 days on average contributed less than 10% to the 4-day total. And if we only used 2 days instead of 3 days, we only got something like 60% of the max values. So that third day was very important. So 3 days seems to be a sweet spot for integrating over time the amount of precip and looking at it from an extreme event perspective. Now, for those of you who live in places that aren't quite as wet, on average, of course, these thresholds don't work as well. And that's where the 100-year return period and that sort of thing comes in. So this isn't meant to be a substitute for that, but an additional bit of information that is more easy to understand and to look at an individual rain gauge data point to see how it ranks. All right, so I mentioned the rest of the country. So one of the early studies, the earliest study on ARs east of the Rockies really came in this case in May 2010, which devastated Nashville with 15 inches of rain or more, up to 20 inches in 2 days, and was associated with a cold front that was coming through that stalled, and also mesoscale convective system, and then training echoes. But also the water vapor that fed into that came in the form of a very well-defined and strong atmospheric river. And this paper showed that contribution to the event very clearly. And as the case with most extreme events for precip, you have multiple things that come together to produce the extreme event. And in this case, we were able to show for the first time that an AR was really a critical ingredient of that. Now let's look at just briefly nationally. 3 examples. There's the Tennessee flood one from May 2010, and the one on the left was record rainfall in the Pacific Northwest in 2006. And here's one you might not have thought of, a storm many people may have heard of called Snowmageddon. February 2010 just hammered the mid-Atlantic states. DC was shut down, for example. Philadelphia, Baltimore, other major cities in the area were really paralyzed during this very devastating storm. And you can see from this integrated water vapor satellite data the absolute signature of an atmospheric river. And we're also now looking at the water vapor transport, and we call this IVT for integrated vapor transport. And on the left, you see the transport for the event above in the West Coast. Here's the one for the central U.S., and here's the one for the Snowmageddon storm. And the color scale here is the amount of water vapor transport per second per meter in an AR. Notice the gray shading is over 1,000 units. This is something we're starting to look at more carefully in our research as one of the key determinants as to whether an event will be very extreme or not in terms of precip. It's basically the fuel for the storms, and we're now looking at measuring this in a more focused way. But this one slide really highlights that ARs are important to the West Coast. They can impact the central U.S. and the eastern U.S. And I want to highlight that a little bit more with a recent paper by David Lavers and Fiorini in Journal of Climate last year, finding basically the Midwest floods of 2008 included a very intense AR, and a significant percentage of the precipitation in the region is also AR related, on the order of 50% or so in some locations. So once again, we're finding this water vapor transport corridor concept, the AR, which on average is a couple hundred kilometers or 400 kilometers wide, is really key. And then also, David Lavers also did a study in 2011, got his PhD in Britain, finding that basically winter floods in Britain are connected to ARs. Very similar approach to what we did for the West Coast. We're now seeing this is true also in the rest of Europe, and this is another paper by David, who's now started working here actually at Scripps as part of our center just a couple months ago, and he's working hard on additional analyses on this topic. So what we're finding basically is that ARs are important in different parts of the country as well, in Western Europe. There are also studies that have been done in South America. Now I want to turn to one technical result for just a moment here. And this is a really exciting advance, in my opinion, where we are trying to figure out what it is we need to observe in order to better monitor and predict ARs. And this schematic shows what we've invented as an atmospheric river observatory. And on the right here, you see a coastal mountain. On the left is the ocean. In this case, this is very West Coast centric at this point. And the blue, big blue arrow is that lowest 2,000 meters or so where the atmospheric river's transport occurs. And then with this dashed line here, we call it the controlling layer. That actually controls a lot of the winds and water vapor transport in that layer specifically has the most to do with controlling the rainfall in the coastal mountains. We also see the snow level schematically shown here in red, which is very important in the mountainous west. When the snow level is high, you can expose more of a watershed to rain and therefore produce more runoff or potentially flooding. When the snow level is low, then you get snow in the higher elevations and you get less runoff immediately. Of course, the runoff comes later when the snow melts. Now, this diagram highlights this atmospheric river observatory technology, and we have a wind profiling radar here, which looks upward in clear air or precipitation or cloud, and it measures the horizontal winds every 100 meters in the vertical. You can see the resolution there. Every hour, we can get a wind measurement like that. It tells us the speed and direction. And part of the reason that's important is because the winds at the surface, they end up being affected by friction and by blocking by terrain, and they are not representative of the flow that's going up the mountain. You've really got to get up above the surface to about 1 kilometer altitude. And we see also a GPS satellite here, which gives us integrated water vapor measurements from a single site using a very cool technology. Okay, so that technology allowed us to monitor ARs for several years, and we have 91 cases now where we found that the storm total water vapor transport, so we know the start hour and end hour of each AR, and we add up all the water vapor that went up the slope, and then we compare that with the total rainfall, and we get this very good correlation. 75% of the variance in storm total rainfall is explained by how much water vapor went up the slope. We were so emboldened by this that we thought we should try runoff. And we did that as well from a stream gauge here at Austin Creek. 60% of the variance in the runoff is associated with how much water vapor went up the slope in that storm. These findings really sweep under the rug all sorts of other phenomena that people have been focused on for a long time. Cold fronts, upper level jets, convection, things that aren't really factored in this analysis. This is the AR conditions are really what are dominating the precipitation and runoff in the West Coast events. This is not true in many other parts of the country, such as the Midwest, where big convective storms are the major player in many parts of the year. But we also saw some examples where ARs may be important as well. California has now invested in a world-class, state-of-the-art, no place else has this, network of 100 field sites to specifically monitor extreme precipitation and the conditions that lead to it, including ARs, including 4 of these atmospheric river observatories on the coast. They run about $1 million apiece, and 10 of these blue squares, which are snow level radars, which run about 50 to 100K apiece, and GPS MET stations, which run about 20K apiece, and then also soil moisture sensors. So this is really the wave of the future for observing the kind of conditions that lead to extreme precipitation and flooding in California, and the lessons from this are being considered for application elsewhere, including the Northwest and farther inland. And the Western Governors Association is very interested in seeing this expanded elsewhere across the West. One could ask, how are ARs going to change in a changing climate? And I want to turn to that as one of the emerging directions. This is a paper, once again, by Mike Dettinger. And what it shows is basically ARs are very much part of the climate in the future. They occur, they continue to occur at about the same frequency, maybe with somewhat increased frequency. The winds in them tend to be a little bit weaker on average, but they carry more water vapor. As the atmosphere is warmer, it can hold more water vapor. But one of the key findings is that because the winds can be strong still in some events, and in the future, and there will be more water vapor in them, the ARs potentially, there will be some that could be stronger than what we're used to seeing. And one of the fun things about this figure I like to point out is notice the date on this top panel here, 18 January 2100. You know, this isn't going to happen exactly that way, right, 100 years from now, but it's showing that, you know, ARs are in the models, a very well-defined one. And this also highlights what I want to mention and forget to sometimes, is that many people on the West Coast have known for years about the Pineapple Express. Well, really what we've done in learning about ARs is put a little bit more scientific foundation on that well-known concept of Pineapple Express, and also been able then to generalize it to more conditions elsewhere in the world, and also to events that don't necessarily, you know, reach out of Hawaii or the southwestern direction. They can come from the west, even from the northwest sometimes, or from the south. So Pineapple Expresses are really sort of a supercharged regional version of an AR hitting the West Coast. One of the other emerging directions is we need to measure these more carefully offshore to evaluate the models, weather forecast models and climate models. And this is a schematic from what we call the CalWater 2 experiment, where we're planning to take aircraft and a ship out to measure these ARs. You see the AR in the background, and to measure them very carefully over the West Coast as well when they hit shore. And this white area is a region of dust coming over from Europe that from Asia, that we've started to see evidence of in the precipitation in California. And there's a nice paper in the journal Science by Creaming et al. That shows our first study on this from CalWater 1 experiment. Now with CalWater 2, we're going to try to measure both of these as they intersect one another. Aerosols are important because they are the little bits of dirt, basically, and a particle in the atmosphere that the clouds first form on that then can grow into precipitation. And we're learning that the character of those aerosols, how many there are, what altitude they're at, what they're made of chemically, really matters in terms of forming precipitation. So this study is now getting started, and we had an early start campaign last February with NOAA's G4 aircraft, jet aircraft, and this was a case we studied in February. And you see the AR coming out of Hawaii hitting California. It produced about 12 inches of rain or more in some locations, gave some drought relief. Thank goodness this event happened. It was pretty much the only game in town last winter. And it produced, you know, something like a third of the rain for the year. And we saw the first real runoff on the Russian River. And another thing, I won't go into detail, but this subtle feature, we call it a frontal wave, we think is really a key forecast challenge. It's a topic of research right now. And then you see the white area is the area we flew the P3 or the G4 and dropped dropsondes along these white lines. And here you see a picture of the G4 aircraft from NOAA and many of the crew. This aircraft's going back out again this winter, along with the NOAA P3 and a ship. And then we have a proposal to NASA to go out for additional winters. We need to capture enough cases that we can really do a systematic and statistical comparison with the model forecasts and climate models. An example of how much of a problem this is that the forecasts of heavy precipitation, we did a study in California and the West Coast that of the 16 events in our study that produced over 5 inches of rain, only 2 of them were predicted to be that extreme just one day ahead. We need to make those forecasts better. Secondly, we've learned that ARs, the landfall position is off by an average 500 kilometers with 5 days lead time. We need to do better with that. So, and also the climate models, depending on the resolution of the model, the transport of water vapor varies by like 40%, and nobody knows the right answer. So those are the sort of the drivers for this major field study that we've proposed and are getting underway here. I wanted to say thank you for the opportunity to present this. This is a picture from that Aravaipa Creek in Arizona. And Henry, if there's a few moments, I have a couple of current slides, or not slides, but some current data relevant to the storms that are hitting the West Coast right now, if you guys would like to see that. Would you like me to show some of those?
Sure, that would be fine, Marty. I just put 2 on our website, connection to the Esrael page, which shows some real-time monitoring of, and I guess forecasts for these atmospheric rivers coming in, so we'll link to that as well. But yeah, okay. that would be great. And I've got a quick question for you, as long as you're putting those up. I noticed this morning a vigorous low pressure system off the New England coast. with those nor'easters, do you ever get atmospheric rivers kind of wrapping around those and hitting the east coast in the northeast? I know you mentioned the snowmageddon, but how about this type of storm?
Yeah, that's a really good question, and I think the answer is going to be yes. In many cases, that's true. The studies to prove it, I don't think, have been done yet. That snowmageddon storm's a case, suggesting it's possible. And a young scientist, Jason Cordera, professor at Plymouth State University, is looking into ARs in New England, and has already got some preliminary findings suggesting that is true. So it would be interesting to take a look at a handful of nor'easters and see how that plays out.
And Marty, you showed the ARs were along or disengaged, not disengaged, but along the cold front south of the low pressure system. How many miles usually, or kilometers, is it typical for them to be apart from the low? So say a low was coming up, are we looking 200-300 miles from there?
Okay, so let me actually go back to the PowerPoint and show you.
And you may want to wait to answer these. I didn't mean to interrupt your.
No, that's fine. I think since we've got this up right here, I can show you that. Can you see that full panel?
We can see the left one, pretty good part of it. Yeah.
Okay, so here you can see our composite. There's the low pressure center in the Gulf of Alaska, and it can be 1,000 kilometers away from the low pressure center.
Okay.
So it can be very severely displaced. There are situations, of course, where the low is wrapped up and the AR, the occlusion point hasn't moved forward as much, that may be less far away. But that's very typical to be 500 to 1,000 kilometers away. And the AR itself, the back edge of it is essentially at the cold front, and then it extends out into the warm air about 300 to 500 kilometers on average. And in the West Coast, what that means is, because the storms tend to move from west to east, not always, but on average for these winter storms, that an AR typically lasts about 20 hours to 24 hours as the storm is passing over. And when they stall and last for 48 hours or more, that's when we get the flooding kind of conditions. Can you see the picture here from CoCoRaHS?
Yeah, looks good. Thank you.
Okay, so this is the current data, and you can see the very heavy precip along the coast here, with totals in the 2 to 5 inches. If we go to the National Weather Service Mesonet, you can see the 24-hour totals. We've got a 5-inch total here off Point Cape Mendocino, Northern California. There's the Oregon-California border, and 5 and pushing 6-inch totals up here in southwestern Oregon. This is great news for the drought in Northern California, but it also has a pretty sharp southern edge. Look at that, 0.02 inches. It just really, that's the southern edge of the AR, essentially, not moving as far south. And then we also have this new network of integrated water vapor measurements in California, and you can see the centimeters here, 3 centimeters or more up in that region, and only 1 to 2 centimeters down here where it's not raining. And then I wanted to highlight the, let's see, this is let me go to this. This is the loop of water vapor from an SSMI site, and this is the current case, and you can see how it's formed up. Here's the beginning as of 3 or 4 days ago, and you see the AR forming up. Started raining like crazy up here, and now it's raining in this region. So this is an example of an AR hitting the West Coast, and up in here I was looking at some of the Mesonet data, and there are places that had received 10 or 14 inches of rain in the last several days, with a number of sites over 4 inches in the last 24 hours alone. So we've got an event underway, and what does this look like for the future? This is a nice graphic and forecast prototype from Jay Cordera and myself, showing the probability of AR conditions over the next 10 days. This is a 10-day forecast out to 240 hours, and this is different latitudes. And the latitude, the position corresponds to the coast, and each of the squares is filled by the ensemble information of whether or not AR conditions are present and how many of the ensemble members. And here we see the dark red is 100% of the 21 National Weather Service ensemble members showing AR conditions over 250 units of IVT in that 12-hour period. And notice there are 1, 2, 3, 4, 5, 6 of those periods in a row, and we see that number 6 at the coast. So what this is showing us is that the forecast right now is for at least weak AR conditions to be present more or less off and on over the next 2 to 3 days on the west coast, in this part of the west coast, stretching down to about right here. Now, 250 units is sort of the weakest version of an AR. We can go to 500 units, and what we see is the moderate strength AR conditions are underway over the next 24 hours. If we go to 750 units, there's really not as much action, and nothing in the 1,000-unit range. 1,000-unit events are very rare. 500-unit events are not that rare. 250 units are several per year at least will occur on average. And if we get 6 of these in a year in Northern California, we've probably got an average year. If we get 4, it's a drought. If we get 8 or 10, it's a flood year. So let me go back to the mimic here and just leave that on. So I'll wrap up with that, Henry.
Thank you very much, Marty. Boy, this is interesting stuff. You don't hear a lot about it, and I appreciate you taking the time to show us this today. I got another quick question for you. Other countries, so you think about the west coast of Europe and Western Europe and stuff, similar events occurring in that area off of...
Yeah, Europe, Western Europe can get hit very hard. In fact, I don't know if anyone's heard about Britain last year or a year and a half ago got just really the wet. I think they broke some 500-year records, and they actually have records that go back 500 years there. And it was AR conditions that were responsible.
Let's go ahead and start taking some questions in for Marty. We're gonna take those right now, and if you'll just type them in with your name and state as well, and we've got some coming in as we speak. And here is one from Gary in Wisconsin. Gary is actually with the Weather Service, and he wanted to know, could you speak to whether GOES TPW, either sound or image derived, could help better define AR given the frequent observer observation availability over land?
Gary, that's a fantastic question. In fact, it was one of our early analyses in a paper by Ralph et al. 2004 in Monthly Weather Review. I'll refer you to it. We actually looked at that, and we looked at TPW from GOES, and we had about dozens and dozens of cases. And the problem we had is that the high clouds are often present over the AR conditions. And because of the TPW derivation method, those high clouds preclude being able to derive TPW from GOES. And we found that the edges of the clouds tended to correspond with the edges of the AR. So disappointingly, the GOES TPW basically wasn't as useful a product as we had hoped. I'm sure there are some exceptions to that where the upper clouds or there's not enough clouds to interfere with it, but that cloud problem is an issue.
Thanks. Here's one from Chris in Texas. He wants to know, is the integrated water vapor data and images available online for the public to view?
Yes, these data are available online. I just went to the website here that I'm showing from SIMS, a research lab, and then the one that Henry mentioned from the Earth System Research Lab, and then we have one here also at Scripps.
We'll put those up on Chris. We'll put those up online later on this week, and you'll be able to have those under the resources part for this talk. Okay, here's another question that's come in, and this one here, they're wondering how and does the atmospheric river interact with the jet stream? Another question is what's the relationship with the jet stream? Somebody else has written. So there are a couple of jet stream questions.
Yeah, let me go back to the PowerPoint for just a second and answer that because we happen to have it right here. Can you see the right-hand panel on that, Henry?
We can see just below the warm, humid. So you have an A and an A on there, and that's about as far south as we go in that picture.
How about on the right side now? Can you see the right-hand panel?
All we can see is where it says cold air and warm, humid air is at the very bottom of the picture.
And then can you see the top part?
We can, yeah, as far as going over to about 600.
Okay, so this answers the question on the jet stream. This is a cross-section from A to A prime on the left, and on the right is the cross-section for the baseline on the left. And the blue contours is the upper-level jet at the high altitude, 45 meters per second. And then down low, you see the pinkish area. It's cut off at the bottom, it sounds like, but that pinkish area is the AR. And the cold front stretches down below the upper-level jet. So that basically the AR is down at low altitudes, below and a little bit to the warm side of the upper-level jet stream. Does that answer the question?
That's great. Yeah, thank you. Okay, here's one in. Tom in California wants to know, are there any studies as to how to control an AR? Is there any weather modification, or are we just sitting ducks where they will land?
Well, nobody I'm aware of knows how to control the weather in terms of the storms and the like, although there are many, many people who've tried over decades to seed clouds to produce more precipitation, but that has been a controversial subject, with some people saying it's successful and thorough studies saying there's no way to prove it. But there's some hope, I think, in that long term. But no, we can't change the storms themselves in terms of the ARs.
Okay, Larry from Kansas writes in, and he wants to know, can the AR path be predicted, and how far into the future can the event be predicted?
That's an excellent question, and let me go to another slide if I can get to it quickly here. The models do have ARs in them in their forecasts, and let's see if I can find the slide. There it is, right there. Okay, so can you see the graph on the left here, Henry?
We can, yes.
Okay, so what this shows is a study looking at forecast lead time out to 10 days ahead, and the root mean square error in the position of AR landfall on the West Coast. This is using 3 winters of numerical weather predictions verified against the satellite-derived AR positions using an objective automated method. And you see the NCEP, or National Weather Service model, Canadian, Japanese, UK, and European Center models. And they all show this trend where a day or two ahead, we have something on the order of 300 kilometers uncertainty in the landfall position. At 5 days lead time, it's about 500 kilometers on average, and at about 8 or 10 days lead time, it's up at 800 kilometers. That's like saying the forecast today is for, today the forecast for 5 days from now is an AR is going to hit Seattle, when in fact it'll hit instead Northern California, or vice versa. That's the kind of size error that represents at several days lead time. The good news here is that the models very much have these ARs in them in the outer forecast times, but they have a lot of uncertainty as to where they're at and how strong they'll be.
Thanks, Marty. Here's a question, actually 2 different questions, one from Jim in Missouri and one from Bruce. And Jim's question is, do tropical systems hurricanes have an AR relationship? And Bruce wants to know, does the current AR have anything to do with Hurricane Anna out off northwest of Hawaii?
Boy, it's a great question, and the answer is, let me go to this image. Can you see that satellite image?
Yeah, pretty much. Yep, there we go. We can see the low pressure system on the left now.
Yeah, so there's Hawaii. At the bottom is Hawaii. Can you see that?
Now we can see Hawaii. Yeah.
Okay, because I can't see the whole screen. I got to scroll a bit.
Yeah, that's pretty good right there. We got the Hawaiian. Yep, and you're showing California as well.
Okay, so let me go up a little bit. So this is the high cloud band that's above the AR, like the question about GOES. That's a classic situation. And you may recall from that other satellite data that we could see the AR right underneath there. So yeah, you can actually see what looks to be a connection. At least geographically, they're not far from one another. And there's a nice study by Jason Cordera and myself and others. I mentioned Jay earlier at Plymouth State that that showed that the storm track north of the hurricanes can be impacted by the hurricanes in a way that changes the AR behavior. So unlike what we initially thought was that the hurricane may have fed water vapor directly into the AR that then got swept up and moved to the west coast, we didn't see that happening as much as we saw the heating from the hurricane at high altitudes changing the storm track in a way that favored the development of a strong AR to the northeast.
Okay, thank you. Here's one for Matthew. Wants to know that is there a relationship between ENSO and AR? El Nino bringing warm water up along California, does that have an impact on the Pineapple Express?
There are two impacts I'll mention. One is the primary, and that is that El Nino has a well-known connection to the storm track more generally. And the ARs are part of the storm track. They're part of the storms themselves. So where the storm track goes is what determines where the ARs go. And because El Nino can influence whether the storm track is to the north or to the south in the winter on the west coast, for example, it very much does impact ARs. The second impact is interesting, and El Nino in that respect is the tropical and western Pacific, not right along the California coast. Some El Ninos come with warm water right along the California coast, like in 1998, the big El Nino did, and we flew the P3 out there, as I showed you earlier, and we actually measured the extra heat and water vapor that came off of that coastal water and determined that it fed it strengthened the storm, the precipitation as it hit the coast. So it does, and by 25%, we believe, in terms of the convective available potential energy. So we do see impacts of El Nino on ARs, both in terms of where they occur, where the storm track occurs, and then also in some cases where El Ninos come with the warm coastal waters, they can sort of supercharge the storms right as they hit the coast.
Here's one from Peggy, and Peggy writes, if you could compare an AR to a strong low-level jet, if you could.
Yes, okay.
Seems like the same thing, but go ahead.
Yeah, so the low-level jet is really the wind part of an AR. So you can have a low-level jet, but it happens to be fairly dry air, so it's not transporting as much water vapor. Or you can have a fairly weak low-level jet, but it's just chock full of water vapor. So looking at the low-level jet's important, but it's really only part of the story.
And here's another person writing in wanting to know that the big floods back here in northern Colorado in 2013 and back in September, was there any relationship to the flood event and related to an AR?
No, that's a really good question. When that storm initially hit, we took a sort of preliminary look at it, and given it's over the continent, we don't have the advantage of the satellite data to look at, so we really can't say from that perspective. There are aspects of it that may be AR related, but I think it's more likely that other processes were far more important in that case.
Bob writes that on one of your slides you showed depicting Cat 1 through 4 events with large red dots indicating Cat 4 occurrences. He said he noticed one isolated Cat 4 near Detroit, close to the Michigan-Ohio border. There were none other relevantly close to it. Could you explain that event in that particular area?
Yeah, let me see if I can find that slide real quick. There it is. Okay.
Yep, down there, right near the near Toledo, it looks like.
Can you still see it?
Yes.
Yeah, and I'm afraid I've got an old version of the figure. We did some quality control after this, and this one up in Idaho and the one in Detroit went away. So, as everybody who collects precipitation data knows, that there are, bugs in the system sometimes. So, apologies for those. This being an older version, we cleaned those up afterwards. We went back and looked at the data more carefully.
Marty, here's a question from Dave in Arizona, and Dave wants to know, do smaller mountain groups such as the Catalinas in Arizona split the AR and the jet stream? How do they affect predictions?
Wow. I love the Catalinas, by the way. I went to University of Arizona for undergrad. That's a really good question, and the analysis has not been done. I can't refer to a paper, but on first principles, I would say yes, that a mountain range the size of the Catalinas, which for others on the phone is about probably 40 miles long, but it goes from the valleys are about 2,000 feet, and the top of the Catalinas is about 9,000. So it's a very tall mountain range, and about 40, I don't know, maybe 40 miles wide. I would believe that the ARs would largely flow up and over because they are prone to going up and over mountains rather than around them. But also we're finding about this inland penetration thing. So yeah, I think there's a connection, but it hasn't been shown scientifically yet.
Here's a question from Cindy in New York, and she wants to know, is the source of AR always in the same geographical location for a particular place, i.e. Pineapple Express comes from Hawaii, but are there other sources of AR that hit a particular part of California?
Yes, in fact, I don't have a nice figure. I can't find it right away, but I have a nice figure in a paper on that. And for California, let's say, or for the West Coast, we found examples of three types, I would say. One that comes almost from west to east. Another that comes from southwest to northeast. That would be like the Pineapple Express kind of typical. And then others that actually come almost due south, from the due south. So the short answer is no, they don't just come from one area, and that's pretty much it.
Dan in Washington, he's on the Washington coast once, he says that one of your slides showed the highest 3-day rainfall totals in California and southern Oregon, yet the annual totals in northern Oregon and coastal Washington are higher. Is this related to AR intensity or frequency?
Yeah, that's a really good question, and I think it's related to the fact that the farther south we go, we tend to have a little bit more water vapor available, and the storms that we've been studying have stalled more. In addition, we know that there are a lot more frequent smaller storms that are not AR related or don't have ARs in them that hit the Northwest. And there was another figure I want to highlight in just a second here. Here it is, where we see in the Pacific Northwest, you know, the dark blues, which are more like 20%, that sort of goes to green in the 30% range. So about a quarter of the annual rainfall falls in ARs up in that region versus 30 to 40 or even 50% in parts of California. So I don't have a great answer for that, I'm sorry, but it's a good question. I'd like to think about that some more.
Henry, I think you muted yourself instead of unmuting yourself.
Yep, there we go. I hit the wrong button. These systems that come in on the West Coast, a lot of thunderstorms, or are they just like a steady rain that comes in with these as they approach?
Yeah, thunder is fairly rare in them, quite rare, I would say, and you know, relative to other parts of the country, especially. Yeah, the rain rates on an hourly basis are not what you'd write home about in the eastern part of the country. A half an inch an hour rain rate, but it can last for a day or two, and you end up with, you know, 2, 4, 5, 8, 10 inches of rain in a day or two. And if you end up with another one coming on its heels, you can end up with these 15 or 20-inch events.
Thanks. Here's Jordan from the Southeast Regional Climate Center, and he wants to know, how often do ARs originating in the higher latitudes occur for the western U.S.? Are these weaker due to less available water vapor?
Yeah, another good question, and I'd say yes, they do originate sometimes in the higher latitudes, but they're really starved of water vapor because the air is just not as warm and not as doesn't start off with as much water vapor. Some of these storms clearly, you know, I'm sorry, I'm stumbling here. the way these storms work, the cyclone forms, it has the cold front, and the warm sector is drawing warm, moist air from the lower latitudes and pushing that poleward. And on the backside of the low, it's taking cold air and pushing it equatorward. That's the job of the extratropical cyclone in the global circulation, is to try to move the warm and cold air around to equalize the gradient. So, so in the process of moving that air around, normally the ARs that form in these situations will be more moist and warm. So the more northern tracts are less moist.
Okay, we've got two more questions here, and we'll kind of end with that for the day. Chris from Texas writes and says, the 3-day precipitation map, let's try that again. The 3-day precipitation map shows lots of extreme events in Texas. Are these due to ARs or some other mechanism, some other event?
Yeah, these are due, we haven't studied it in detail, but it seems most likely that they're due to either landfalling hurricanes or tropical storms, which really are not ARs, or not AR related exactly, or they're due to the big thunderstorm complexes that can form, and last for 12 hours or so in some of the worst cases in the summer or spring. So as we showed with the Nashville event and the recent David Labor's work, it's clear that ARs can play a role, but we haven't unraveled that fully yet. I'd say if I had to guess, most of those are tropical storms.
Okay, we did get a couple more questions that have popped in here. Jim in Missouri wants to know, do tornadoes have an AR relationship, direction and intensity? Is there anything with these ARs that spawn tornadoes?
I think there would be an indirect connection because the low-level jet is very important for tornadoes, significant tornadoes. And also the water vapor, in terms of how much fuel is available for the convective storms that go vertical and very strong and produce the tornadoes. The ARs can feed, are feeding some of that water vapor in. So I'd say they're peripherally related.
Susan writes in, and she says that you mentioned the interaction of aerosols with ARs. Is the evidence of precipitation suppression in ARs during? Is there evidence of precipitation suppression in ARs during some of the pollution episodes in East Asia?
The findings so far, actually, really good question. The CalWater experiment I mentioned, which we're going out for CalWater 2, we started last February. We're going again this January, February. And by the way, there should be something online. You can follow some of the flights if you want to see what we're doing. We should have about a dozen or 2 dozen aircraft flights with a ship out there in January, February this year. The initial going in position on CalWater 1 6-8 years ago was that the air pollution from California in the Bay Area and the Central Valley would go up the slope into the Sierra and suppress precipitation because it would spread the water vapor out over more cloud drops. Therefore, the cloud drops don't grow big enough to fall out. But what we found instead was that air, instead of going up the Sierras, is going up to the north in Shasta, hitting Shasta, and it's in the Sierra barrier jet. The atmospheric river air coming across the Pacific rides up and over the Sierra barrier jet into the Sierra and doesn't take that boundary layer air from the continent in. And what we found falling out in the rain, falling out onto the Sierra, was evidence of dust from Asia. So pollution from Asia could very well get in there. And this is actually a really hot topic scientifically, and it's part of what we're trying to do with our 5-year vision for CalWater 2, is to get the kind of aerosol measurements with the AR measurements that we need simultaneously.
Well, we've got one last question, and Marty, again, thank you for taking the time to answer these. Thomas writes, and he asked he said, great job. As you conclude this fantastic picture of scientific data, could you define an atmospheric river in the most simple layman's language as if you were offering the first lesson in public education?
Yeah, an atmospheric river is a narrow ribbon, a couple 100 miles wide, 1,000 miles long, ahead of the cold front, that is chock full of water vapor and does most of the water vapor transport in the atmosphere in the mid-latitudes. And when that atmospheric river hits the right environment to force the air to go up, either mountains or a cold front or other situations, that can produce some of the heaviest rain we see anywhere.
Well, Marty, thank you so much for taking time out of your busy schedule to be with us today. We really appreciate it. Some great stuff. I know our folks that were on the webinar today really appreciate that and have learned a lot. What we'll do is we'll post your slides when you send them to us up on the webinars. If you have any other links that might be helpful for our viewers, and also we'll have this this presentation that we record today up there as well. So thanks again, Marty. I appreciate you coming on.
Thank you, and thanks to everybody for watching.
For the rest of you out there, please join us on our next CoCoRaHS Weather Talk webinar. That'll be on, mark your calendars, Thursday, November 13th, not too far from now. This webinar will feature Carrie Olheiser of NORISC. That's NOAA's National Operational Hydrologic Remote Sensing Center. Boy, that's a mouthful. And that's just outside of Minneapolis, Minnesota. She'll talk about what they're doing and how your CoCoRaHS observations, especially snow and snow water equivalent measurements, play an important part in their models. And finally, when you guys, as you're signing off today, if you would please take the survey that'll pop up on your screen, just a couple of questions, that will really help us out a lot. So until next time, this is Henry Regis for the rest of the CoCoRaHS team here at headquarters saying goodbye and have a great afternoon. Take care.